Good day, ladies and gentlemen. This is just me trying to explain the mathematical induction proof a bit better. I don't know if this helps, so take it by a pinch of salt, okay? So to summarize, I wouldn't say what the professor teach, but to summarize what I know, when it comes to mass induction, right, there's only three steps, all right? So the first thing is proving the base case. And the second step is assume that case n equals to k is true. And the third is prove that n equals to k plus 1. Yeah, just prove. We need to prove this one. And once you've done these three steps, right, you'll be solid for almost all your maths questions. At least all the questions in this topic lah. Alright. So let's take a look at some of the. Let's just dive into the questions lah. Alright. So let's take this question as an example. So say, okay, first thing about induction is you need to take note that we are not solving an equation, we are proving an equation. I'm gonna write this down here. We are proving a statement. Okay, this is what we're doing, and we are not solving equation. Okay, it's very easy to see this because you'll realize what's given here, right? There's actually an equal sign in between. It's not like they're trying to tell you to solve this, you know, they're trying to tell you to prove this thing, prove this whole thing. Okay, so now let's dive into the actual solving part. All right, so let's take a look back at what I mentioned here. First one, okay, before we actually start to hear, right, okay, we need to state the statement. So we say that Pn, usually P denotes a statement, and this is not equal sign, it's just a colon. Okay, Pn, the statement says that n over k, the summation lah, okay, up to k, 2k minus 1 is equals to n squared. We can basically cancel this whole part because this whole part is just an iteration of this. What I want to say here truly is actually to prove that this will lead to this. This is what the question is asking about. So how do we prove that? Let's just start with the solution, okay? First step, prove the base case. The base case is very simple. Find the smallest value you can for this part here. So you can see that k equals to 1. K cannot be 0, right? So we just say that we need to prove that p equals to 0. P equals to 1. So what is this? So it's 1 over k, summation of 1, 2k minus 1. Okay, now this part is, my bad. Just reiterating, this is a colon, not an equal sign. Okay, equal sign here. This will basically sum 2, we sub k inside, right? This will become 1. Now, technically we solved here already, but this is not enough. We want to prove that the left hand side equals to the right hand side. So now this is our left hand side. What is our right hand side? Right hand side should be n squared, like this. This is what you call proven. Okay, you can see that from here it leads to here when the case is 1. Maybe I just highlight the n here for you all to see. This is n, this is n, and this is n. So you can see it's the same thing here, here, and here. Okay, now base case is proven. Step 2. What was step 2 again? Oops, sorry, it should be this one. Step 2 is assume that n equals to k is true. Alright, so assume n equals to k is true. So what do we do? P, k, alright. Actually, this is a very confusing letter. You know what? For this situation, I'm just gonna use R for this question, okay? But in the future, if I come across this question again, I'm just gonna change the letters, okay? Prove that n equals to r is true. Okay, so how do we go about this? So basically, again, keyword is assume. We're not gonna prove anything, so it's very simple. R k equals to 1, 2k minus 1 equals to r squared. Just like that. That's done. That's all. That's literally assuming. We don't need to prove anything. Now the hard part is this one. When we say that we want to prove it, right? This is the hard part. We need to prove that n equals to r. Sorry, this one in the future. R plus 1 is true. Okay, yeah, we just prove this, okay? So let's do this. P r plus 1. What would this be? It will be r plus 1 summation. Okay, this is k equals to 1. 2k minus 1. Okay, what does this equal to? This will equal to k equals to 1, 2k minus 1 plus 2 r plus 1 minus 1. This is a term. This is the r plus 1 term. I hope you all can understand this part. You all can see that initially is r plus 1. We sum to r plus 1, but now we sum to r and we pull out the individual term outside. Okay. Now here's the interesting part. What you can see here is, because we assume this initially, okay, you can see that it's equally the same here. So this is the part where you can sub whatever you assume. Okay, I'll just draw it more nicely because it's very important. You can sub whatever you have assumed into this part. Whoops. You can sub whatever you have assumed into this part. So what does that give us? That will give us, okay, the first one will be an r squared plus, this one will be 2r plus 2r plus minus 1. Whoops, this is very, whoops. Okay, yeah. Something's not right. Yeah, it's just 2 here. Okay, then this will leave us with r squared plus 2r plus 1. And surprisingly, this will give us 2r plus 1 squared. Now, you can see that in this case, right, once again, we have proven it already. When we have sub in r plus 1 here, we have r plus 1 here, and we end up with an r plus 1 square. It's just like this. It's just like the initial statement here. Exactly the same, right? Oops, that's not a well drawn one. Give me a moment. Go CD here. Okay, yeah. So with this, right, we have seen that it's proven. Okay. Now technically the working is here. It's basically done already. But for induction, right, we actually have to add 2 more lines. First thing is, we need to say that P r plus 1 is true if PR is true. You can see this is why. We assume the step 2. If the step 2 doesn't hold, we cannot sub in the results into step 3. So we need to say that PR plus 1 is only true if PR is true. Now this is our first sentence. What's our second sentence? Since P1 is true, our base case, so we can say that Pn is true for all n larger than or equal to your base case 1. Okay, take note. Sometimes, right, your base case can start with 2. If that's the case, right, then you need to put that n equals to 2. Sometimes a base case can start with 0, then it should be 0 here. But basically, this whole page right here is the solution for one single question. Alright, now, hope I got that recorded or solid. Alright, let's look at this second question here. So this second question, right, it's probably what I mentioned just now. A base case, a bit different. So once again, let me draw this out first, just a line. Okay, this one, for this question, right, let's start a bit differently. Okay. Oops, can we do it here? Okay, yeah. Alright, so let's say the question, right, give you this. A plus AR plus AR squared plus until plus, oops, plus ARN equals to ARN plus 1 minus 1 blah 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 R minus 1. Yeah, and it says that prove this is true. Now, the front part here, right, usually, at least for me, right, I'll find it very redundant to write it that log. So I would like to put it into a summation series as in the front here. So we can just say that n, just like this, j equals to 0. Yeah, good job. This time they use R, which is my favorite letter, at least for these induction questions, okay? So I just put it ARJ, okay, equals, oh yeah, sorry, this is my PN, ARJ equals to ARN plus 1 minus 1 over R minus 1. Okay, we need to prove this thing. Okay, let's go back to these 3 steps. Prove base case, assume case n equals to k is true, and prove that n equals to k plus 1. Okay, let's start. Step 1, prove base case. Okay, so you see that in this case, the summation, right, it starts from 0 now. Just now we start from 1, now we start from 0. So P0, what will it be? 0, j equals to 0, ARJ. So it will be just AR to the power of 0, which is just a single letter A. Now, as I mentioned before, we cannot just put this up. Even though this is solved here in normal maths, right? It's solved. Hey, good job, you know. We should get our marks 2 points. But in induction, right, we cannot stop here. We need to show this in the form of this. So what can we do? We can say A times R minus 1 over R minus 1. Because anything, the same thing divided by itself, we get the same thing, correct? So what this will give us is A R minus 1 over R minus 1. But this is still not good enough. We need to show that this is actually power 1. And because we started from 0, we need to end with 0 as well. So it will be A R 0 plus 1 minus 1 over R minus 1. Now, take a look at what's going on here. As I mentioned just now, n, and there's an n here. Now we have, let's use a different highlighter, pink color, let's go. We have 0, 0, and 0. Can you see the pattern here? This is what's called you've proven your base case. Okay, now second step. Assume k is true. This is the easiest step. You all should be thankful that this is part of the solution. Assume n equals to k is true. So just write pk, summation of k, j equals to 0, arj, skip all the working. This is true, so ark plus 1 minus 1 over r minus 1, done. Step 2 done. Now, step 3 is a part that will get a bit tedious. So I'm just gonna write over here, just for simplicity. Okay, prove n equals to k plus 1. How do we do that? Pk plus 1, it will be summation, correct? Summation up until j, from j equals 0 until k equals 1. Yep, k plus 1. This one I didn't write so well. Okay, so as I mentioned just now, this will basically be the summation up till k plus ar power k plus 1, the j term, the k plus 1 term. Okay, so as mentioned just now, I just use the same color, green color. Okay, we know that this is exactly the same as this, so we can sub directly this into this. Amazing, right? So let's continue. Let me think. How should I write this? Yep, I think I'll just do it this way. rk plus 1 minus 1 over r minus 1 plus a r k plus 1. Okay, now usually, right, up to this part, the third step, right, it's a lot of algebra and just summing around, but you can sort of see the pattern. What we're trying to prove, right, is we want this format, okay, of the original statement. We want to show this thing initially, right? So technically speaking, we want to show this thing as well for our k plus 1 k plus 1 scenario. Okay, so I'm not too confident about this, but let's give it a shot. I'll pull out a first. So this will be just rk plus 1 minus 1 over r minus 1. So this will be just rk plus 1. But because I want to make it the same denominator, I will times an r minus 1 and also times an r minus 1 in the top as well. Okay, now good thing is you have the same denominator. I can pull r1 equals out, r minus 1 out. So inside I'll just have rk plus 1 minus 1. This one, when I times, right, I will have rk plus 2 actually, because I times another r minus an rk plus 1. I think we're seeing a pattern here, right? We can cross this and this out. So what are we left with? I think it's getting clearer. We have a r k plus 2 minus 1 over r minus 1. Now, technically, this is not done. Remember, we're going to show the k plus 1. So there should be one more step. A r k plus 1 plus 1, right? Because the term is k plus 1. The thing I want to prove is n plus 1. Yep. So now we prove it. Minus 1 r minus 1. Now this is what you call proven. Because you can see it, let's use orange color. Okay, you can see k plus 1 here, k plus 1 here, and k plus 1 here is proven. Now remember, don't forget to write the last two sentences. Pk plus 1 is true if pk is true. Okay, now since p0, remember base case is 0 now, is true, pn is true for all n larger than or equal to 0. That's your working. Okay, so basically these two are the questions in the book, at least. Alright, let's see what else we have. Okay, some of you have a big questions about like the inequality. I'm not too confident as well. I'll see how I can explain this the best I can. Alright, so okay, one thing I want to highlight to you again, right, is usually your base case is given in the question. Okay, in this context, for all positive integer n, we know that positive integer starts from 1, correct? So actually 0 also works here, but I don't know if they accept 0. Anyway, let's give it a shot. Okay, so our statement is Pn. Remember, it's not an equation, it's a statement. So this is colon. Okay, n smaller than 2n. Okay, let's try the base case. Write it down for clarity. Proof base case. So it will be P0 is your 0 smaller than 2, 0. This is true, right? Because this will become 1. Okay, for inequality, right, I think there's not much to be proven. I think. Let's see. Maybe you can say that at most you can say LHS equals to 0. RHS is equals to 2, 0 equals to 1. So LHS smaller than RHS. Proven. Maybe that's all. That's the best you can do. Okay. Now, second, is super the easiest part. Assume n equals to k is true. So p k, okay, LHS will be k. Actually, no need. This one we just assume it's true. We don't need to write any, we don't need to prove anything. So k is smaller than 2 power k. Lovely. Alright. Now, third part, let's try and work on this together. So prove that n equals to k plus 1. Let's try. P k plus 1. How do we do this? Let's take a look at the left hand side first. Left hand side would be k plus 1. Right hand side would be 2k plus 1. Okay, what we can do here is that 2k plus 1 is actually 2k times 2, correct? So we can say that since this is not conclusion yet, since we know that k is smaller than 2k, then k plus 1 will be smaller than 2k times 2. If you want, maybe what I can explain is because times 2 is greater than plus 1. I don't know if you can see this or not. This is different. This is times 2. Times 2 is always greater than plus 1 no matter how you see it. So it will always be larger. So with that, but then again, once again, right, y'all can see why n equals to k is important. Because this is how we lead to this. Okay, if right, on the other hand, if today k is not smaller than 2k, k is larger than, let's say in this case, okay, I don't know what number that would be, but if this is true, right, your k plus 1 may not necessarily be greater than k times 2. That's this case. So this I would say conclusion cannot be achieved without you assuming that k is true. So that's why once again we need to say that p k plus 1 is true if pk is true, and our base case is 0. Since p0 is true, pn, the statement, is true for all n larger than or equal to 0. That's all. Right? Yeah. Okay, let's look at the next question. Okay, let's see. So now let's take a look at this. Okay, let's paste it here. Alright, so once again, this time this question is quite nice. It tells you that n equals to 1, 2, 3 is false. It gives the base case where your base case is 4. So let's go. P first, before step 1, we need to write Pn first. Pn is 2n is smaller than n factorial. Okay, step 1, prove base case. I'm just gonna write short form lah. Nah, I'm just gonna write full form. Prove base case. P4, what would that be? 2, 4 equals to, let's go LHS, right? LHS equals to 2, 4 equals to 16. RHS equals to 4 factorial, which will give you 24. So LHS is smaller than RHS. Proven. Step 2. Assume n equals to k is true. Pk, so it will be 2k is smaller than k factorial. Done. Step 3. Prove n equals to k plus 1. So pk plus 1, what would that give you? 2 power k plus, let's do it LHS, sorry. LHS equals to 2k plus 1 equals to 2k times 2. Right hand side will give you RHS is equals to, sorry, I'm a bit lost here. Yeah, k plus 1 factorial. Now this is interesting. K plus 1 in factorial is actually k plus 1 times k factorial. I don't know if you realize this. So take factorial Let's go smaller number lah. 4 factorial is 4 times 3 times 2 times 1. So this part is actually 3 factorial. You can say 4 times 3 factorial. If this is your k, this is your k plus 1. So k plus 1 times k factorial, which is this case here. Okay, so back to this. Okay, so k plus 1 times k factorial. This is the interesting part now. Okay, so since we know that the question says that n must be larger than 4. So your k in this case, right, must be larger than or equal to 4. And your k plus 1 will definitely be larger than 4, correct? Which is larger than 2. So, and because I use since up there, right? And 2k is smaller than k factorial. So 2k times 2 is smaller than k factorial times k plus 1. You see? Because k plus 1 is larger than 2. Yep, so that's our explanation. I hope you can see this. This k plus 1 is larger than 2. So this thing will definitely, the right hand side will definitely be larger than the left hand side. Yeah, the left hand side will be smaller than the right hand side. So this is proven. And remember to write your last sentence. Don't forget that. In this case, I'll just draw it out here lah. Okay, I don't think that's enough space. Okay, so pk plus 1 is true. You see, it's almost the same sentence every time. If not almost, literally the same, no change at all. But you just need to write it out. This is proof by induction. Pk is true. Since P4, in this case P4 is true, Pn is true for all n larger than or equal to 4. That's your answer and solution to this question. Alright, that's okay. Let's take a look at this question now. Now we come to division. Okay, this is actually the crazy question. Later I can show you one even more crazier question if we have time, because it's looming into 20-30 minutes now. But anyway, let's go. So this time we're doing division. Okay, it's divisible by 3. What does divisible by 3 means? Basically, if you all remember from last class, right, it would mean that it can be used to times something. So technically speaking, Pn, it means that n cubed minus n equals to 3a, where a is an integer. This makes sense, right? Okay, at least the way I would do it in this case, okay, n is a positive integer. Let's go. Proof-based case. Positive integer P1 then. Does 0 work? Let me take a look. Actually, 0 works as well. I don't know, should we do that? Never mind, let's just do P1 lah. Okay, 1 cubed minus 1, okay, equals to 0, equals to 3 times 0. Done. There you go. That's our base case. Hope you can see it. It shouldn't be like this, but yeah, basically it's on this note. Yeah, not the same here. Okay, now assume k is true. N equals to k is true. So pk, k cubed minus k equals to 3b, where b is an integer also. Okay, now third step, prove n equals to k plus 1. So p k plus 1. K, this is the hard part. K plus 1 cubed minus k plus 1. We need to expand on this. So give me some time. I'm using my maths now. K, it should be 2k here. 2k plus 1 times a k plus 1 minus a k plus 1. So this expand again, k cubed plus 2k squared plus k plus k squared plus 2k plus 1. I hope that's correct. Minus k plus 1. Okay, so now we, power 3, k cubed only, power 2 plus 3k squared. So this is plus 3k plus minus 1, so plus 2k is plus 1 minus 1, so there's nothing left. Okay, so what do we have? Can we sub this into here? Actually, we can. So how do we do that? Technically speaking, we just need to plus another k and minus another k. Then we have already. What does this give us? It gives us k cubed minus k and plus 3k squared plus 2k plus k. Okay, what does k cubed and k? I hope you all can see this. K cubed is here, k cubed is here. So we can, I'm gonna draw this a bit badly this time. Sorry, not this part. We can sub 3b inside. Okay, so what do we have next? 3b plus, okay, this can be factorized. Let me try and think how it is. If I'm not wrong, it's 3k and a k should be, oh wait, what am I doing here? I'm blind. This is 3k squared plus 3k. So in the end, it would be 3b plus k squared plus k. And we know that b and k are integers. So, hashtag proven. There you go. Right, because we have proven that it's an integer, a is an integer, b is an integer. Since b and k are integer, this will be an integer as well. Okay, so you know what, I'm just not, at this point I'm just so lazy to write already. I'm just gonna copy and paste this whole thing, right? You can really tell that it is always the same. Sorry, just gonna paste here. Paste option. Yeah. Okay, just change one. PK is true. Since P for this is P1. Alright. So this case is n larger than or equal to 1. There you go. Seriously, the conclusion part is the same thing. Always the same thing. Never change one. Okay, last question. Okay. What do we have here? This. Okay, you know what? I don't need to show the hard question already. It's the hard question. Right, solid. Let's go. Okay, we got the question here. Now, non-negative integer n, so that means including 0 lah, okay? So let's go. Pn equals to 7n plus 2 plus 8, 2n plus 1 is divisible by 57, so 57a, where a is integer lah, okay? Is integer. Okay, base case p0 lah, because it's non-negative ma. So prove base case. P0, what does it give us? 7, 0 plus 2 plus 8, 2, 0 plus 1 equals to 7 squared plus 8, 1 equals to 56 plus, is this true? Sorry, 49. My math's not mathing. 49 plus 8, which is 57, which is 57 times 1. Proven. A. Okay? Now, K. Oops, not this. Okay. Yeah, y'all can say the magic word with me. Assume n equals to k is true. P, K. What does this give us? 7k plus 2 plus 8, 2k plus 1 equals to 57b, where b is integer. Okay, now step 3. Prove n equals to k plus 1. So what does it give us? P k plus 1. We will have 7. This needs to be careful, guys. K plus 1 plus 2 plus, this is that really dangerous part. It's times 2k plus 1 in the inside and you plus some 1 outside. Okay, so let's see. We have 7 k plus 3 plus 8 2k plus 3. Alright, so as I mentioned before, we want to see how we can get the thing from here to use inside, right? So usually what I would do is 7k plus 2, at least you can see it now, times a 7, right? 2k plus 1, so it will be 8 2k plus 1 times an 8 square, something like that. Okay, let's see what should be the next step here. This would be 64, right? Okay, I think I see it already. So we can say that 7 times 7k plus 2 is plus this is 64 right? 2k plus 1. Now I hope you all know this, can see this thing. 64, if 64 x, right, it will be equals to 57x plus 7x. So in this case, if x is this, right, I'll say that 7k plus 2 plus 7 8 2k plus 1 plus 57 8 2k plus 1. Okay, now you can see that this 2 is the same denominator. We can say 7k plus 2 plus 8 2k plus 1 plus 57 8 2k plus 1. Now magic guys, you can see that this is exactly equal to this. You can see the pattern is starting to come out already. It's always substitutable. So it will be 7 times 8b. Is it? Sorry, 57b. 57b plus 57 8 2k plus 1. But job's not done. What should we do now? We should show in the form of 57 7b plus 8 2k plus 1. And remember, b and k are integers. So this is an integer as well. So once again, we have proven this whole thing is an integer, just like our statement right here, 57a. So again, hashtag proven. And the magic word again, just copy this whole thing lah. Sometimes maths can be, I won't say, it's not really, once you see it, right, it's not really that hard. It's quite simple, but it can be very tedious. You have to go through a lot of steps to get to your final answer. Yeah, it starts from 0 this time. So since p0 is true and larger than or equal to 0, there you go. This is our entire lecture slides example that I've been going through. I hope this helps you all. So see you all next time. Bye bye.